Okay, so if you're having to watch this from home today, it's 417. We're looking at parallel circuits in our honors physics class. So let's go ahead and take a look at this now in detail. It's in your note packet, probably about 3/4 of the way through, because we are nearing the end of this unit. So we again contrast the series circuits with parallel. Series had one device fails, everything shuts off. Total resistance is the sum. Current is the total voltage source divided by the total resistance. Voltage is divided, and so forth. Now we're going to look at parallel now. Voltage across each device here is the same. So because each light bulb is connected to the terminals of that battery, we would say that each of them get the same supply voltage. The total current from the source is divided now amongst the various branches. So whereas series resistors or series circuits had the voltage divided amongst the devices, here we have the current divided. So because they're in a parallel arrangement, the current is divided amongst them. Total current in the circuit is equal to the sum of the currents in each branch. And I want to highlight again this thing called Kirchhoff's current law. And so again, this wasn't formally in your notes, and I might change this in years down the road. Kirchhoff's current law. Essentially, it just says that all the current coming into a node has to equal all the current coming out of the node, right? So if I look at this particular current or that particular node up there, and let me zoom in just for a moment and throw some numbers on this. So in that particular junction, I see 4 wires coming in. And so if you're connecting this up with a series of circuits, you might have 4 wires all connected together. Let's say that I have 3 amperes flowing through here, coming from that battery. I have all these branches that the current could flow through. I see one of those light bulbs has an open switch, and so no current is flowing through there. But let's say that I have 2 amperes flowing through here. Could you reason through, using Kirchhoff's current law, how much current must be flowing through that top light bulb? It'd have to be 1 amp. And the idea there is that Kirchhoff's current law says that the total amount of current coming into that node has to equal the total amount of current going out of it. What would happen if it wasn't if it wasn't the case? What would happen? Those tennis balls would sort of pile up at that node, wouldn't they? You remember passing the tennis balls around. And so if you had more or less current coming in than going out, then you'd sort of have a buildup of charges, if you will, there. And so yeah, that tells us that all the current coming in must be the same as all the current going out. If one device fails, everything still works. Okay, so the nice thing about this is that they all have independent paths. Now off to the right here, I want to take a moment and show you how the equation works for equivalent resistances. So when I have resistors in parallel, the equation that we use to determine the equivalent resistance is the reciprocal of the sum of the reciprocals. And I could have any number of resistors in that. But you might recall doing this with springs when we were doing springs in series. We were like, oh, when we have a series arrangement of springs, we had to do a reciprocal of the sum of the reciprocals. I want to show you that is a direct consequence of this equation. When I have resistors in parallel, what effectively am I changing in that equation? What is it actually changing? Turn and tell that person that you're sitting next to. When I have resistors in parallel, which of these factors is being changed, and how is it being changed? Just take a moment, talk it over. You might recall that in series we said it was effectively increasing the length of the path. You guys recall that? If I had them in series, I'd be increasing the length because everything has to flow through. What am I doing when I add things in parallel? I'm messing with the area. So take a look at this. Just so you guys can see how this works. If I have these two things in parallel to each other, isn't that essentially like making the wire bigger? It's providing more pathways for the current to be able to flow through that. that's effectively increasing the area, like the cross-sectional area. So the more paths I give, the bigger the area becomes, the smaller the resistance. Right? So the more pathways I provide, the bigger the cross-sectional area, the less resistance I have. So when you start adding resistors in series, you increase the resistance of the circuit. When you start adding resistors in parallel, you decrease the overall resistance. And you'll see that that works out using this equation. You'll see that as we go through and do some examples. All right. Did you guys know that your houses are wired in parallel? Raise your hand if you've ever done anything with household wiring. Okay. The houses are wired in parallel. You know that because you can turn your light on in your bedroom, and that doesn't turn on your alarm clock or whatever. You can turn your light off, and it doesn't shut down something else over here. These things can work independently of each other. As more and more devices are connected to a circuit, there's more current in what are called the line wires. So I'm going to take a moment and make sure you understand why we have circuit breakers and why we don't want to plug in lots of things into a single outlet. Current's excessive overheating can result in a fire. The picture to the right is showing maybe a typical circuit that might go to, could be a kitchen area. In that kitchen area, you have some heater going on. Maybe it's a portable heater. You have a lamp there, and then you have a toaster plugged in. If I add up all of those currents, I notice Kirchhoff's current law says 20 amperes coming in. 20 amperes coming in. Some of that goes this way, some goes this way, some goes that way. What if I then take and add another device in here? Put a hair dryer in here. Let's keep ourselves going. If I add a hair dryer in here and it pulls 5 amperes, what does that do to the line current? The current flowing through it increases it from 20 to 25 amps, right? Say it again. It overloads it. And of course, that's where you get a fire, right? So the idea here is safety fuses. They melt when you given current is exceeded. You might have seen fuses that look like this. Probably where you have seen something like this in the home is probably down near an older furnace. Okay, so furnaces are going to have some safety fuses here. You have to unthread that, replace it. If that thing blows, you'd have to replace it. Now, fuses are very common in cars. Raise your hand if you've ever blown a fuse in your car. If you've got a fuse box there and a fuse blows and something doesn't work, right? Your trailer hitch, sometimes it's trailer hitch wiring, whatever the case is. When that fuse blows, you have to replace it. One of the reasons I said when you're using the ammeters that you hook it up correctly, make sure that you are not hooking it up in a parallel arrangement, is that you will short circuit your devices and then you exceed that current reading and it blows that fuse. Now, in most cases, things have been replaced with automatic switches. Automatic switches are circuit breakers. Essentially, many of these things work based on temperature, right? And so I'm just going to say it's like a bimetallic plate. These things are made up of 2 different metals, and when they have current flowing through it, they expand at different rates, and often what happens is when I have too much current, they'll just open up. And so the nice thing is that they can cool down, and then when they cool down, they'll close back. But a lot of them, they're done with what's called a bimetallic plate. Okay? Now you can, once they trip, they're going to open, they're going to stay open, but then you can manually reset it. If you reset it and the wires haven't come back together, it's just going to go right back open, right? And that's just because of the way that they've been designed. Now some of them are more electronic than that, but they used to be just a bimetallic plate. Okay, I'm going to show you guys how to do a couple of problems via doing an analysis here, and then we'll give you guys a few problems to try on your own. Okay? All right, let's take a quick look at this one. Again, the copy that I gave you guys did not include all the words there. It's supposed to be analyze the following circuit, determine the equivalent resistance to the total current, and the voltage drop across each device. So sorry that didn't all make it on there. Here I have a 1.5 volt battery connected up to a 5 ohm, 10 ohm, and 15 ohm resistor that are written in parallel. I wanted to add this to your slide. I'm going to do this right now. And so please, as a little side note, if you have identical resistors in parallel, This is a very convenient way of analyzing resistors that are identical, that are drawn, that are in parallel. Let's say that I have 4 resistors, all of the same value. Let's say that they're all 40 ohms. So every one is the same, all connected together. Would you agree that each time I add another resistor there, I effectively reduce the equivalent resistance because I'm adding more area? If I have 4 identical resistors all connected together, that would turn into an equivalent resistance. That would be equivalent to a 10 ohm resistor. And how I know that? Well, let's just do the math really quick. It's 1 over 40 plus 1 over 40 plus 1 over 40 plus 1 over 40. Would you agree that that's 4 over 40? And then I take the reciprocal of 4 over 40. What's 4 over 40 reciprocal? Is that 10? So effectively what I've done is I've taken those 4 resistors, all of 40 ohms, and I've cut it into 1/4 as great. And so you don't have to do a lot of math with that. As long as they're all identical, the final resistance would be like 1/4 of the original resistance. What if I had 3 resistors and they were all 60 ohms? 3 resistors, all 60 ohms. So again, these are as an aside, so that we don't have to do a lot of fancy math here. If they're all 60 and I have 30, and I have 3 of them connected together, the equivalent would be how much? Divide that in thirds, right? So 60 divided by 3 would be 20. That would be an equivalent resistance of 20 ohms. So that would be equivalent to a 20 ohm resistor. And again, that equation, 1 over Req is equal to 1 over R1 plus 1 over R2, 1 over R3, is very simple to solve when you have identical resistors. When they're not identical, we have to do that math. But oftentimes when they're identical, we can just go through and do that fairly quickly. All right, let's go ahead and determine one Req. First thing I'm going to do is I have to write that equation out. 1 over Req is equal to 1 over 5 ohms plus 1 over 10 ohms plus 1 over 15 ohms. There's no easy math here. You have to add them together. Now, instead of using your calculator for this, could you find the LCD, the least common denominator? Would you agree it's what is it? Is it 30? Mm-hmm. Okay, so the least common denominator is 30. So 1 over Req would be equal to 6 over 30 plus 3 over 30 plus 2 over 30, over 30, which would be equal to 11 over 30. So if the equivalent resistance is if 1 over the equivalent resistance is 11 over 30, Req would be the reciprocal of that. Which a calculator would be handy here, because I can't do 30 divided by 11 in my head. It's 2, what is it?
Oh, I don't know.
2 point something.
7.
Is it like 2.72 repeating or something? Yeah. Okay. Now, I want you to look at that resistance is actually less than the smallest resistance there. You guys notice that the 5 ohms is the smallest one of those 3? When I add more and more resistors to that, what I'm doing is I'm reducing the overall resistance. This will always be less than the smallest value. Let's say that you've made a mistake and you go through and you do your calculation and you come up with a number bigger than the smallest value. You've made a mistake. Okay, so that's just a little check for you. Now what I'd like to do is I'd like to determine the voltage drop and the current through each device. Well, would you guys agree all of these things have the same voltage drop? All of those things have 1.5 volts across them. They're connected directly to the battery. So delta V is exactly the same. I from the battery would be equal to delta V divided by the equivalent resistance. I have a 1.5 volt battery and the equivalent resistance is 2.72 ohms. So if I want to get the current from the battery, I take, again, V over R, 1.5 divided by 2.72. I'm getting about 0.55 amperes. On your diagram, will you draw that as electron current flowing from the battery? On your diagram, draw that 0.55 amps as electron current flowing from that battery. Not conventional current, electron current. See if you're able to do that. It would look like this. The electron current's going to flow from the negative terminal, sort of in a counterclockwise fashion. Remember, positive or like charges repel each other. So if that's the positive plate, that's the negative plate, then the electrons are going to be flowing this way. Typically, we draw it as conventional current, meaning we think of it as coming from the positive, but in reality, it's the electrons flowing that way. Now, some of that's going to go up through here. Some's going to go through here, and some's going to go through there. I want to determine how much flows through each one. So how do I find I1? Is I take the voltage drop across it divided by its resistance. How do I find I2? I take the voltage drop across it divided by R2's resistance. And so you should be able to do that for all three of those resistor values. So let's go ahead and try that together. I flowing through 1 would be equal to delta V over R1. 1.5 volts. That's 5 ohms. I'm getting about 0.3 amperes through that one. I2, same equation, same voltage, different resistance. I didn't need a calculator for that. I'm dividing that by a number twice as big, so I should get a number that's twice as small. And so 0.3 is now 0.15 amps. And for I3, the current flowing through that one should be 1/3 as great as that, because I'm dividing by 3 times that resistance, 0.1 amperes. And when I add them together, sure enough, all of these add to 0.55, which is what I'm sort of expecting. Okay? So I can get the current flowing through each one of those devices. You can give you a lot of space there. I apologize. I could probably make these a little bit bigger, but that's how you go through and solve that. Could you go through and try that bottom one on your own? See if you're able to get through it. I'm going to put the answer on the board without doing a lot of talking, so you guys can work without me talking. Give it a go, and then we'll see if your answer compares. If you're watching this from home, you should try to solve this one as well on your own while you then check your work with me afterwards. Okay, so if you're trying that video from home or trying that solution from home, you should have gotten those values for all of the resistances and current going through those. Always check to make sure that your total current adds up to the current from your individual branches, and that's a good check. Do you guys notice that when you're doing the 1 over REQ equation that you don't have to do it in kilo ohms, you could just leave, or you don't have to write it out as 10,000 ohms and 2 kilo ohms or 2,000 ohms, you just leave them in kilo ohms, and then when I'm done, my answer is 0.625 every kilo ohms. Then I convert that into ohms when I'm doing the other thing there, okay? How'd you do? Were you able to get it? Okay, you have a few problems to try on your own, only 5, I think. They're in your packet. A couple of them on the back have an ammeter in it. It's in my 2nd hour, 5th hour. We're having some questions on this problem, so I want to take a moment and make sure that if you're confused on anything, you're able to get that resolved. So I want you to turn in your packet, if you would, to the parallel homework. Can I borrow yours for a second, your parallel homework? The confusing question was this one here. So number 5 is one of the problems that I'm going to have you do. It's a 440 volt battery of some sort. That is an ammeter. What that means is they've put a device in this thing that measures the current flowing through that particular branch is 20 milliamps. That means it's 0.020 amperes flowing through that. Now, what you're doing over here is you're determining R total. That's the same as R equivalent, right? So R equivalent is the equivalent resistance for that. I2 would represent the current flowing through this branch. I total would be the current flowing from the battery, right? But people were confused by what that meant. Okay, so for that one, that's an ammeter. I think the problems that I had you do for this one, go back to this here. Okay, so if you want to circle these, that'd be great. It would be 1, 3, 5, 6, and 8. 1, 3, 5, 6, and 8. Again, probably take you 15 minutes or so. Try to have those things completed by tomorrow. I'm probably going to check them, right? I want to see that you've made an effort on those things. So get those done by tomorrow, please. And then we'll move on into combination circuits, which is both series and parallel in the same circuit. So we have to know how to do each one individually. I'll show you how to do them together. All right, that's where we are.